we completed the discussion of isomerism, and then we had seen the few examples that how ethanol and dimethyl ethers are isomers, how the connectivity is different. That's why we say constitutional isomer, because constitutions actually is changes. So like propanol, isopropanol, methoxyethane, this chemical composition is same, but compound is different. And of course, there is in the structure. So we discussed that, and then we try to understand that how actually why stereochemistry is so important. And then we try to understand that thalidomide disasters because of this RS configuration that happened in the history. Due to that, we give the weightage to the stereochemistry that yes, we should understand the structural perspectives. And then we try to discuss that what is the constitutional isomerism. So how constitutional uh, isomerism we can define, and then how the isomerism we can define. And then stereoisomerism, how diastereomers, enantiomers, and the cis trans, conformer, rotamer. So now so let me start with one example, that when we say the connectivity. So let's see the example. If I say you have two compounds. Now let's see, we have two compounds. One is we have ethane, and this is you have this compound is ethane, and this compound is the ethene. So what is the basic difference between these two? What we can see here at this point of time, that what is the hybridization of this carbon? So your hybridization of this particular carbon is sp3. And what about the hybridizations at this point? It is sp2. Okay, that's fine. We understand that what is hybridization, how sp3, how when we have sp3 at this point, then you have a 4 bond. When you have a sp2, then you have a 3 bond. Now my next question, that this sigma bond is formed how? Means between the sp3 and what kind of orbital of hydrogen? So can you tell me that how this sigma bond actually it formed here at this point of time, at this particular, if I will say this one, and if I say that this is a sigma bond, this red color one is a sigma bond, so it is, so absolutely correct, Deepak. So basically your s orbital of this hydrogen, means your s orbital, if we say so basically your S actually is spherical, and at this point you have a sp3 orbital, then actually it overlaps together, and finally your s orbital and sp3 orbital both actually combine together, and then this hybridizations, this the bond sigma bond appeared here at this point. So now about this carbon, if I say about this carbon, how many orbitals at this particular carbon, like if I say C1, how many actually orbital? If I talk about C1, so this is the C1. So how many total orbital at C1? Means how many orbital is in sp3? Total number of orbital? 4. Okay, Utsav, correct. Okay, it's a 4. What about now? I will tell this C1 is at this point also at C1. So this C1 is now what kind? How many sigma bonds you have? How many sigma bonds at this C1? 3. So here you have a 3 sigma bonds. So basically, if you see this bond is sigma bond, and this bond is also sigma bond. And now if you say this bond is also sigma bond, but now once you have a double bond at this point, this already these three sigma bond is at this point. So what this all three sigma is formed because of the sp2. Then what is remain at this point? So you have a s, and then you have a px, then you have a py, then you have a pz. So now your s orbital and px pz will mix together. So what we can see here, when sorry, so your this one will mix and then it will form the sp2, s sp, and then you have a 2. So this sp2 and then you have remaining is the pz. So what we can see here at this point, when we talk about ethene, means when double bond is there, then you have a sp2, and sp2 is how many orbital? sp2 you have a total 3, and then one orbital is pz. Now if I say that what about pz, whether pz is a hybridized orbital or it is an unhybridized orbital? My next question is that whether pz is a hybridized orbital or unhybridized orbital. Yes, it's unhybridized. It didn't participated right now in the hybridizations. So it's a pure orbital and it's not hybridized, but these three orbitals is the hybridized orbital. So now you have a these three is going to have a 3 sigma bonds, 1, then 2, and then 3. You have 3 sigma bonds, and then this pz orbitals and this 1 2 3 sp2, what angle we can expect between these two sigma bonds? What angle we can expect? When you have a 3 lines, then what angle we can expect? Of course, geometrically we can expect 120 degree. That will be the most stable. So you see, not 109, not 60. Okay, because 109 when it will form, when the 4 bonds will come, like here. When sp3 will come, then 109 will come. But you see, when you have a 3 lines only you have a 3 lines, then the ideal situation is that it should have a 120. So that is the reason that this angle is 120. And if this is 120, then this all 3 sigma bonds will be in one plane. So what is interesting part here? This all 3 sigma bond is in one plane, and then your pz orbital. Now your pz orbital will be perpendicular on it. So what I'm saying, this is actually the pz orbital. So your pz orbital is this one. This 2 is a pz orbital, and that will be perpendicular on the trigonal planar system that formed because of 1 2 3. So what I am trying to say, the geometry of ethane and geometry of ethene is very different. Why it's different? Because here you have a sp3 which requires a 109 degree angle. Because 109 degree, because you see, you must have all the bonds separated apart as much as possible. And that is the reason mathematics, actually whatever the mathematics will allow, that much it can go. So 109 degrees is possible, and that is the reason that it will form a tetrahedral arrangement. So that is the reason that when we talk about sp3, then it's become sp3, and that is a tetrahedral mathematical arrangement and 109 degree. But when we go for sp2, then we see trigonal, and we see the angle 120, and we see the planar structure. So we see planar sp3 tetrahedral. So you see, when molecular orbitals actually helps us to understand the structure. So that is the reason that we are trying to understand the structure. Now, second thing, when you have this kind of a structure, then what happens basically, uh, this partial overlap between these two orbitals, and this orbital, when this orbital actually overlaps like this, and actually this overlaps these two, then a partial bond forms here. So this bond forms, and the down also the bond forms. So a trigonal planar, and then on the top and the below, actually it forms a electron cloud, because now you see your electron cloud is actually perpendicular here and here, here and here. So like a sandwich kind of a structure. So means your sigma bond right now, this sigma bond here, rotation is free. Why? Because this is single bond, there is a no restrictions. But when the partial overlap will come at this point, so let me draw. So I think drawing may give. Okay. So basically what I am trying to understand here, that when you have a carbon and you have a like this structure, then this pz orbital is perpendicular on it. Then you have a plus and you have a minus, suppose, and this is the orbital. So this is actually perpendicular, and what will happen? This will partially, this electron will share together and share together, and by that way this bond, what was single bond, that is now covered on the top also electron cloud, and on the bottom also, below also electron cloud. So this electron cloud actually restrict the rotation between this carbon. So actually your C single bond is rotation is free, it can rotate. But when you have a double bond, then rotation is restricted. So what basically we are trying to understand, whenever you have a formation of double bond, so basically the electron cloud is like this, like this, then your this single bond rotation is now restricted because it forms a double bond. So when your suppose your carbon is single bond, now your hydrogen is here and your chlorine is here. Now your, suppose your hydrogen is here, now chlorine is here. But this rotation is free. So I can draw this structure now, here chlorine and here hydrogen, and here hydrogen and here chlorine. So either I can write here chlorine, or at this point hydrogen, or I can draw hydrogen here. I can, no problem. Why? Because we are talking about a single bond. So this rotation is free. So this rotation is free. So this hydrogen and chlorine can interchange together, and that is the reason rotation actually restricted rotation cause isomerism, cause stereochemistry. And that is the reason that this stereochemistry we would like to understand. So how we can understand? We can understand with one example. Now let's see. Let me see example. Yes. Now you see, suppose I say this hydrogen A, and this hydrogen is now you have B. So hydrogen A and hydrogen B is very close, but because of this rotation is free, after some time this hydrogen may come here, and this hydrogen, this, sorry, and this hydrogen will be here. So you see, either this hydrogen or HA can interchange together. Why? Because rotation is free. But at this point, suppose your HA is here, then your HA cannot come at this point. So your HA will be remain at this point. This is actually restricted rotation because of this partial overlapping of this unhybridized p orbital due to that double bond formations. And we try to understand this one by sp3 and sp2. Sp3 tetrahedral because 109 degree, and sp2 you have 120 degree and planar system. So now let's see the 3D looks also at this point. Now suppose you have a double bond at this point. At this point you have a double bond, and now this is the real alkene molecule. Real alkene molecule. Let me copy it. Control C, and then let me go here on 2D, and then you see here. So basically what I'm trying to show you, this is on plane, this is on the plane, and here actually we have a pz orbital that is perpendicular on it. So basically you see the complete plane. This is complete plane in one plane. So if you have here some other groups, example, suppose you have whatever the group, suppose you have chlorine. Suppose here you have a chlorine. So here you have a chlorine. So now this chlorine cannot come at this point. It will fix because rotation is restricted at this point. So that is the reason when you have this kind of a group, rotation is restricted, then there is a possibility of the isomer. That is your cis trans isomerism. And that if you see example, I didn't draw a slide example. So let me show you in PowerPoint slide. So the example. So now if you go here, so now stereochemistry of carbon-carbon double bonds. So now let's see, you have a compound number one, this one. So this compound number one, where 2-methyl group is the same side of this double bond. And if you see the compound number two, now methyl group is opposite side, this two. So why this one and two is now different? 1 and 2 is different. Why? Because here rotation is restricted because of the presence of sp2. That is the reason that this 2 isomer is called geometrical isomer, or I say this one we can call it cis isomer. This one we can call it cis, and this one we can call it trans. So it is easy to say cis trans because only two group is here. So what we are saying right now, alkenes have a 2 adjacent sp2 hybridized carbon, and these carbon atoms together with the 4 atoms which they are attached are coplanar. So we understand why it is a coplanar. Bond rotation and restrictions that makes these two compound is different. Now tell me whether one can convert to 2 or not. This is possible. One can convert to 2. Yes or no? No, it cannot convert because, as I say, rotation is restricted. So Aditya, it's not possible to convert these two directly without any chemical interventions. Why? Because, as I say, that this rotation is restricted. So this methyl group is on the same side. It will remain same side. It cannot interconvert like this. So if you have a single bond, then it is possible. Why? Because CC single bond rotation is free. Then it is possible to interconvert, but not under this situation. So that is the reason that these keywords, what we have written here, that is a non-interconvertible. Why? Because rotation is restricted. So we are trying to understand these two is two different things, different compounds, complete different. These two is not same exactly because this is a cis isomer, this is a trans isomer, and cis and trans cannot interconvert with each other. Why? Because this rotation is restricted. Now my next question, whether 1 and 2 can superimpose on each other. क्या हम लोग इसको एक दूसरे के ऊपर रख सकते हैं? Can 1 and 2 can? No. So basically these two are not superimposable. So if I say, what is the definition of diastereomers? Chalo, if you talk about memory, then what is the definition of diastereomer? What is the definition of diastereomer? What is diastereomer? In one line, what I can say? Do you, anyone having any idea? Yes. Non-superimposable, non-mirror image. Matlab, it should not be mirror image of each other, and it should not be superimposable also. That is diastereomer. So my next question, whether these two are mirror image of each other? No, these 1 and 2 are not mirror image of each other. Now next question, 1 and 2 is superimposable? No, 1 and 2 is not superimposable. Can I say 1 and 2 are diastereomer? Can I say 1 and 2 is diastereomer? Yes. we can say diastereomer, but it is better to call cis trans. This is more popular, more common. So what we try to understand here, that what is cis trans isomerism, why it happened, why we call it diastereomer also, why we have used a keywords non-interconvertible. So we try to understand all those things. So this is basically the geometrical isomer also we call. So all the synonyms we try to understand. Now my next question, 1 and 2, which one is more stable? Why 2 is more stable? Why 2 is more stable? Good. You all know very well the answer. So why 2 is more stable? Yes, trans is more stable, but less repulsion. I agree. I agree. So you see, in a very simple way, I don't want to go in right now detail, but actually it is related with heat of hydrogenations. When you hydrogenate this one, this will convert to butane. This will also convert to butane, 1 mole of hydrogen, then energy. Based on the energy, we can tell experimentally, we can prove that yes, 2 is more stable. But I don't want to go in detail like right now in the experimental part. Just very simple. These two methyl groups are so close, and that is the reason here maybe we have a bad contacts, and these two methyl is far apart. So these two doesn't have the bad contacts, or I can say steric problem is not there, or in your words, steric hindrance is very, very less in case of 2. That is the reason that 2 is more stable, but experimentally it is well proven using the heat of hydrogenations, and by the experimental fact also we know that 2 is more stable. Yes, thermodynamically stable when we calculate energy. So when we calculate energy based on the experimentation, so that's why I say that experimentally it is proven. Okay, so anyway, we are trying to understand cis and trans. Now let me tell you one thing. If it is a cis and trans, then if you have a more number of groups at this point, then it is very difficult to say cis trans. Example, let's see here. Now in this case, if you say here, it is very difficult to say cis trans. Why? Because with what respect we need to say cis trans? Here you see, here we say cis trans because we know methyl group is the same side. That's why we say cis. And here methyl group is opposite side. That's why we call trans. But when we go for this compound 3 number, then with the help of methyl group, we can say trans. With the fluorine bromine, we can say trans. But with the respect of fluorine and methyl, we have to say cis. So you see, it's a kind of a relative sentence, cis and trans. So the best way this kind of a confusion we can avoid using our nomenclature using E and Z. So using E and Z, yes, Rohan, EZ configurations, correct. So with the help of EZ configurations, we can talk, and E and Z is basically the priority. And that is actually can in gold pre-log rule, CIP rule, and with the help of CIP rule we can number it. We can number it the priority. How we can number it? Because this carbon is connected with fluorine. So CIP rule, what it says that in the fluorine and methyl, which will get the first priority? Can you tell me? कौन किसका नंबर 1 होगा, फ्लोरीन का कि मेथिल ग्रुप का? As per the CIP rule, fluorine will get the priority 1. Absolutely correct. And carbon will get the priority 2. So I agree with you that you are correct. Methane is wrong. Why? Because this carbon is connected. You see, carbon is connected with fluorine, and here carbon is connected with carbon. So carbon and fluorine, which will get the priority? Of course, fluorine will get the priority. Why fluorine will get the priority? Because atomic number of fluorine is higher than the carbon. That is the reason fluorine will get the priority as per the CIP rule. So 1 will go to the fluorine and 2 will go to the methyl group, because methyl group means carbon is there. Methyl group is what? Carbon is there and hydrogen is there. हाँ, क्लास खत्म करके कॉल करते हैं, है ना? ओके. So yes, when you have a carbon double bond and you have a hydrogen and deuterium, in that case what happen, atomic number is the same but mass number is different. So that's why if we have a situation when atomic number is same, then we can go for mass number. So because mass number is 2 and here mass number is 1, so we can check the mass number. So this kind of a situation when the atomic number will be same, then we can check the mass number. But in most of the cases, we can go for atomic number. So by that way, we can easily check which one will get the what priority. So anyway, now I was talking that fluorine will get the priority number 1, this carbon will get the priority number 2, and in this case, bromine will get the priority number 1 and methyl will get the priority number 2. Now with the respect of with this double bond, now we have to check whether the first priority group is opposite or the same side. If your first priority group is opposite, then that is called opposite. Opposite, the word is actually ng gen, so this reflects E. That is the reason that E pronounce E, and nomenclature we use E configurations. So because your first priority group is opposite, that's why E prefix use in nomenclature. And this E is nothing but it's a stereochemistry assignment configurations. And now in this case, you have a priority number 1 and methyl priority number 2. Now bromine priority number 1, methyl priority number 2. So now one priority and the bromine one priority is the same. So this is called together and the word is called Jusaman, and that is the reason that we call JED, and that is the reason that EZ configurations we tell. Now my next question is that E or Z, why we call configuration? Why we call configurations? Why not conformation? What is difference between configuration and conformation? Why we call it configuration? Why we call it EZ isomerism or EZ configuration? Configurations cannot interchange. Conformations can. So configurations cannot change. Why? Because there is a restriction. But conformation can change. Why? Because there is a single bond, rotation is free. So when we talk about double bond, rotation is restricted. And that is the reason that this compound number 3 and compound number 4 cannot interconvert each other. And because of these properties, because it cannot interconvert, that is the reason we say configurations. We avoid to use conformation because conformation actually interconverts. So that is the reason that we talk about non-interconvertible. And that is the reason that we call it EZ configuration. Now compound number 5 and compound number 6, what we call compound number 5 and compound number 6, whether these compounds are cis trans or EZ or both. Compound number 5 and 6, what we can call, whether we can call cis trans. 5 is what, cis or trans? Okay, and what about 6, whether 6 is E or Z? So 5 is cis and 6 is trans, or I say 5 is Z 6 is E. Of course, we can say both. So you all are absolutely correct. So we can call it cis also, we can call it Z also. Good. So I hope that now we understand that how we can explain EZ isomerism, cis trans isomerism. So that configuration also we understand, conformation also we try to correlate. So now in the case of there is any possibility in the case of ethane no 5 and 6 are 5 either cis you can call 5 or you can call Z. So if you say cis, then also it is fine. If you say Z, then also it is fine. In the case of 6 also, you can call it trans or you can call it E. Both is fine. So only I am saying that some cases where E and Z is more appropriate. Like in the case of 3 and 4, cis trans is not good to represent. What I'm trying to explain you all that I would like to explain that in the case of 3 and 4 compound, it is better to explain with the respect of only EZ. But in the case of 5 and 6, it is good that to explain either by cis trans or EZ. So when we need to use मैं क्लास ले रहा हूँ, क्लास के बाद आपको कॉल करता हूँ. ओके, मंडे को देख लेंगे, है ना? नहीं नहीं, अभी कोई जरूरत नहीं, मंडे. ओके. So I was saying that in the 3 and 4, it is better to explain by E and Z, and 5 and 6 by both way we can explain. So Nishank, what you would like to ask? Can you say your questions? Can you type again exactly what you want from me? Nishank, can you type what means what you didn't understand? Three, in the case of 3, how you can say cis or trans? It's very difficult, na? Because in 3 case, if you are saying cis, then in what respect you have to say cis? Cis means you have to say under what case you are saying cis. Cis means same side. So cis doesn't represent the first priority group is the same side. But E says first priority group is opposite. Z says first priority group is same side. So E and Z is more precise. It says exclusively that first priority group is same side. But cis is saying that two group is same side. So cis is not saying that which particular group is same side. But E or Z is explaining which particular group the first priority group is the same side, because total you have a 4 substituents, two left side, two right side. So whether these two same priority group, the first priority group is same side or opposite side, that exclusively answered by E and Z. Cis and trans cannot answer exclusively this. That is the reason that 3 and 4, we cannot say cis or trans. That's why in the name, in the case of you see here, we have exclusively written Z. So anyway, subset is not a very good word to explain these things. So better that cis trans we can use at some place, and E and Z is the more absolute term. Whenever we say cis or trans, we have to say, like if I want to explain this compound number 3 with respect to cis and trans, then I have to say fluorine and bromine is trans in the case of 3. So I have to say whole sentence. And with respect of methyl group, or with respect to fluorine, or with respect to bromine, we cannot conclude cis or trans, because that is a confusing. So that is the reason that in the case of 3 and 4, cis trans is not recommended. Only E and Z is recommended. But in the case of 5 and 6, our old nomenclature system, cis trans, is perfectly fine. You see, slowly when we get the more and more example, more and more complexity, we came out with our better nomenclature system. So EZ is the more precisely explain the structure, or in towards more absolute, I say. And cis and trans are much more relative stereochemistry. So if I say relative, and relative means we have to always compare. But when we say EZ, exclusively 1 to CIP rule will come play the role. That is the reason. I hope now you are able to understand when we can use cis trans, or of course wherever you can use cis trans, where definitely EZ you can use. But when you are using EZ, and that time you will try to explain with a cis trans, maybe it may not be a recommended choice. So I hope now we are able to explain the EZ and cis trans isomerism. Now let me go about the tartaric acids. I had given you the brief introduction also before that about this tartaric acid, what is optical activity. So I don't know whether you little bit you have refreshed your previous book or chapter or not, but tartaric acid is one of the example. I can say birth of optical isomerism and chirality is actually explained by tartaric acids. So let me, I will come back on tartaric acid later on, because it's a 4 carbon and it's a 2 chiral center. So let me come back on tartaric acids later on. First, one more thing is that whether I need to explain this polarized light or this definition of optical rotation, or you all are fine, or I should say some 1 or 2 lines. Optical activity, like I will say that what is optical activity, can you explain it? Or I will say that what is chiral compounds, what is chirality? So these things I hope that you know it, but if you have a doubt, so okay, fine. So you want me to say something on it, so I can say that, you see, uh, when you have a light source, then you have a this you have an ordinary light. If I say a vector quantity which is going 360-degree everywhere, so this ordinary light, when you pass through polarizer, so what will happen? Polarizer will have a effect so that your ordinary light will have only 2 directions, up and down. So means you have a just plain linear polarized light, or I say plain polarized light. So actually you have converted your light source to a single direction. And this single direction light, when you have converted, that light is called plane of polarized light because you have a plane of polarizations. Now, in between, when you keep your sample, suppose your sample is here. So what will happen? You have supplying a linear polarized light which having a single direction. So your light is, so basically your light source is giving you light. Your light is coming like this and you have a sample is here. Now, when light will go and it will pass and it will go straight, means your sample doesn't have any effect on the light. So once you don't have any effect on the light, means that compound doesn't have any role with a plane polarized light. So because you have polarized this light in a unidirectional, that is the reason that we say that you have a polarized light because you have used a polarizer. And now if your sample is chiral, then what we observed experimentally, this light may go right directions or may go left directions. So both direction is possible. This is purely experimental phenomena. Means when you have a sample in between the polarized light, then only you can observe this kind of a optical activity. So this is purely experimental phenomena. This we can conduct in our lab. That instrument name is called polarimeter. That instrument name is called polarimeter. And in the polarimeters, now so much modern instruments are now available. Even in our laboratory also we have so much modern instruments, and we can test any compounds, whether any compounds having optical activity or not. So if like a layman, I can say this compound is optically active. How we'll test it? We cannot say verbally. We have to go in lab. We have to keep our compounds in a sample, and then we have to see whether lights, polarized light, plane polarized light, whether when it comes out from the sample, whether it goes right side or whether it go left side, or whether it won't affect. Three cases is possible. If it will go right side, then I will say that it's a dextrorotatory. If it will go left side, we will call it levorotatory because it rotated the light in the left side. That is the reason that क्लास ले रहा हूँ राकेश जी, कॉल करता हूँ फिर. So both case is possible, or another case is that it may not rotate in its directions, either left or right. That is called the sample doesn't have any optical activity. So this is optically inactive and both case is optically active. Now next things we observe that this compound, if it is chiral compound, then only this kind of phenomena comes. Means optical activity is, now we understand it is related with chirality. That's why we try to understand optical activity, chirality in a same chapter. We try to understand. So now we understand what is optical activity and how it is related with chirality. So this is basically the example of optical active compounds. So now there is a three cases possible. One case, this can rotate the plane polarized light. This case also can rotate the plane polarized light, and this may not, because you see this structure and this structure is actually mirror image of each other. So that's why these two is called enantiomer. This is not mirror image of each other, these two. That's why this one and this one is called diastereomer. Another thing is that this compound, when you keep in the sample, then plane polarized light won't rotate. However, this compound is chiral. So this compound is chiral, but still optical activity is not there. So there is a internal compensations, there is a plane of symmetry, and due to that actually it happens. But anyway, I don't want to right now go in detail. I would like to say, yes, this compound is chiral, but still optically not active because of some mathematical symmetrical nature. And due to that, we call it mesotartaric acids. meso compound, because it's a chiral. It's a chiral, but it's not optically active. So what is chirality? So basically we are trying to understand the mirror image, or like one hand and this is the another hand, both is mirror image of each other. Both is mirror image of each other, but both is non-superimposable. So this kind of a compound which having this kind of a relations, that non-superimposable relations, that is called chiral compounds. So generally chiral compounds are optically active, but there is a case when chiral compounds also not active, optically active, and this is the one of the example. So with these two slides, we are trying to understand what is optical activity, how it is related with chirality, how we can explain with an example also. And what is dextrorotatory and what is levorotatory. Dextro means when plane polarized light will rotate right side. Levorotatory, when we talk, then that is left side. So these things we need to remember, that when the plane polarized light rotates right side, that is called dextro, and when left side, levo. Okay, so now one more thing I would like to ask you, what is this capital D? What does it mean? Why this capital D is here? Is there any reason to have a capital D at this point? You see, this is the name tartaric acid. This minus, what does it mean? What is significance of this minus? What is the significance of this minus? No, I'm talking about this minus. This minus means left side. This minus means it rotates plane polarized light in the left directions. That is called levorotatory. So when minus is there, it means the compound is rotating in a negative side, left side. Minus for levo and plus for dextro. So this minus plus means this one. Now can you tell me what is this SS? What is that? What is this RR? What is that? Now my next question, how many chiral center in this compound? How many chiral center in this compound? We have two chiral center. We have two chiral center in this compound. How many total carbon we have? 1, 2, 3, 4. We have total 4 carbon. But how many chiral center we have? We have only two chiral center. We have only two chiral center. So this two chiral center should have its own name. That is the name by RS configuration. So this one will have a S and this one will have a S, and this is SS, and this one is R and this one is a R. That's why it is RR. And this one is a R and this one is a S. That's why this is RS. So if this is 1, this is 2, this is 3, this is 4. So 2 is R, 3 is S. So what I'm trying to tell you, that how we can explain exclusively about this particular carbon, how we can distinguish these two, we can use absolute configurations. Absolute configurations. And one of the example is RS configurations. RS configurations. So total 3 compounds you have: number 1, number 2, number 3. Right now you have a total 3 compound. So all 3 compounds having a different name. All 3 compounds having a different name. All 3 compounds are tartaric acids, but all 3 compounds having a exclusively different name, because all 3 compounds are a different compound. So you have cap DSS minus tartaric acids, this one having a RR tartaric acids. So how we can name this compound as a SS, how we can name it RR, how we can name it 2R, 3S, that we need to understand. So our next object is to understand the RS configuration. And if I say, like example, if I say that compounds, suppose you have a can you tell me this is R or S? Can you tell me this is capital R or capital S? Okay, so okay, I agree. S is correct. S is correct. So capital S is correct. Now if I say R is not correct. So anyway, we will discuss in next class. We will discuss how to assign RS configurations, and this RS configurations actually will be in your quiz also. So in the next class, we will try to discuss about the uh, RS configurations, and then how we can assign D and L configuration also. So can you tell me this D, this D is not dextro or L is not LIGO? Okay. So this D configuration and L configurations and R configuration, S configurations, these things we will discuss in our next class with an example of glyceraldehyde. So D and L configurations, yes, correct. D and L configuration is a relative configurations and RS configuration is a absolute configurations. So basically DLRS configuration is very important, that we will discuss in the next class in detail, and I hope that you all will be able to answer them afterwards easily without any problem. You can answer. So yes, first let me finish my next class. Afterwards we will decide a quiz. Okay. So once I will complete DL configuration, RS configuration, thereafter we will keep our quiz. So first let's first understand. Okay, this is my second class. So after third class only we will think about the quiz. Okay, so I hope that you are able to understand what I am conveying to you all, and in the next class we'll finish the DL RS. Thank you. Then I am just concluding today's sessions, and maybe I will put one demo quiz for you so that you can try that one in the team. So that demo quiz will have a 0 marks and you can try. Okay, so I am concluding now today's sessions. Thank you.